A video for homework 19, problem 1, hints. Here's the setup that we have for this thing. A strategy to solve this for the reactions here would be, I want to start out and get the mass moment of inertia about B. We'd start by doing 1/12 the mass of this whole thing, which was given as a single mass, right? Because it's just one bar. But these two lengths are given. So for a bar, it's 1/12 ml squared, but we have two different lengths. So we go LAB plus LBC squared. But that's at this spot right here. So if you want to get the mass moment of inertia about that spot, you have to add in m, and then the distance between the center here and here. Well, that's going to be this average length, right? So LAB, I'm not going to fit it onto this then, LBC over 2. But then you're going to subtract out that length right there. So minus LAB squared. All right, and then you get the value for this. Let's draw the FBD and the IBD. Drawing this thing carefully and thoroughly is a really important part of solving these problems. Helps you think your way through. Here's our coordinate system. All right, let's take a look at our forces. We have our weight acting at the center, more or less. I can't remember if this is in US units or in ISI, so I'm just going to go mg right there, or we could put the weight. And then right up here, I'll put the reactions. So here's RBX, RBY, and then lastly we have a force down here, FC. For the for this right here, we're going to have I, and let's go. You know, a lot of times, even though it doesn't quite matter where you would locate this, all right, so I'm going to try to fix that line. Let's go ahead and put it up here and say, because it's IB alpha. Oh, you know what? I'm sorry. I forgot. That's not at the top, is it? It's like right here. All right, so I ruined my pretty little drawing with my erasing, and now I ruined it this way too. All right, let's try to be neat. So it's like somewhere right there, right? So there you go. There's IB alpha. But then we also, remember, we have the mass times acceleration in the x direction. And because it's going to interfere with up there, I'm going to draw the line, the arrow coming and touching it there, going M-A-Y. So summation of moments, take them about B, is equal to IB alpha. And remember, we can only write this because this is the type of problem, this is the constrained motion type of problem. And so the only thing we have here, and I'm going to insist on making counterclockwise positive, we have negative FC times the length LBC, and it's going to be equal to, and then negative IB alpha. And we don't need to do the distance here because we don't need to do the virtual thing right in there to be able to get, we don't have to do the effective moments in here because we went ahead, because it was the special case where we could move the moment of inertia to be about B. So just from that, we can solve what alpha is going to be because we know everything. Now we go to the sum of the forces in the x direction equals mass times acceleration in the x direction. So we could find the acceleration in the x direction is just going to be this little distance between here and here. All right, so I think it's LAB plus LBC over 2 minus LAB. That will get times alpha right there, right? So that'll give us this value. And so we'll be able to get Rx. And then the one that you probably didn't remember, mass times acceleration in the y direction, there is angular velocity on this thing here. So the acceleration in the y direction is going to be omega squared. And then that same value right there, the LAB plus LBC over 2 minus LAB. Right? So you'll be able to get their reactions, RBX and RBY, and then just find what the magnitude of them on that RB. It's going to be the square root of RBX squared plus RBY squared. End of the video. Should be able to get the answer. So it's not that different from the example in class with just a few slight variations, not much. You should be able to get the right answer.